solid phase transitions. John.
Thanks very much, John. And thank you very much to the organisers for giving me this opportunity to speak. So I'm going to talk about things which are clearly free boundary problems. You see in these pictures here lots and lots of interfaces that are obviously free boundaries. Though I must say I don't really think of them as free boundary problems. And I don't think people who work in the area think of them as free boundary problems either. And that's probably because we don't understand enough about them to apply the necessary techniques. So the general philosophy behind those pictures that you see there, various different materials, is that the free boundaries between the different phases that are involved are driven by geometry. It's a kind of microgeometry or a geometry at the mesoscale, which follows from the requirement that the different phases, which have different shapes, fit together at the mesoscale, so the deformation gradients corresponding to these different phases are compatible. And along with that comes the fact that the model has got to predict that there are interfaces anyway, which means that it's not an elliptic model, if you like, which would give rise to smooth deformations, and that's expressed in terms of the variational language by saying that the free energy density is not quasi-convex. Quasi-convexity, I'll explain, or I'll try to explain, is the central convexity condition of the multidimensional calculus of variations. And so the fact that the energy is not quasi-convex leads to the formation of infinitely fine microstructures in the models which I'm going to be using, which ignore or put to zero interfacial energy. So there's a sort of plan. Okay, so you can read it. Okay, so Martin-Zittig phase transformations. These are all microstructures that the pictures all come from Martin-Zittig phase transformations, which involve a change of shape of the crystal lattice of some alloy at some critical temperature. So, for example, it could be cubic to tetragonal, so there might be a critical temperature, theta critical, and when theta is bigger than theta critical, we're talking here about single crystals, so a perfect crystal lattice. So above this critical temperature, the material might be in its high temperature phase, which is called austenite, and it might be cubic, so that the typical unit cell, for example, might be face-centered cubic with an atom at each corner of the cube and an atom in the middle of each face, repeated periodically. And then you reduce the temperature through this critical temperature, theta critical, and due to the interactions between the atoms and the electrons and all this sort of stuff, the material wants to change its shape. So the cube in this case gets deformed to a tetragon, which is a prismatic object with two sides equal and one side different, and there are three possible ways that it can do that, which are the same according to the crystallography of the original situation. It can, for example, the longer side can extend in each of the three cubic directions. So you get three what are called variants of the low temperature phase, which is called martensite, so three tetragonal variants. So now, so lots of different phase transformations can take place. Another very common one is cubic to orthorhombic. In this case, the change of shape is different. So here's the the elementary cube again. And so now you stretch it in one of the cubic directions, and then by different factors in the two face diagonal directions. And that gives you 6 possibilities. You've got 3 choices here and 2 choices for which of these 2 stretches is given. So that gives you 3 times 2, which is 6 variants of the martensite. So here's a picture, a high resolution picture of a cubic tetragonal transformation in nickel manganese. And so just looking at it, you can see a sort of piecewise affine deformation of the material. This is below the transformation temperature, so it's in the low temperature phase, martensite. And you see that there are layers separated by vertical interfaces. So here I should say that each dot represents a column of atoms perpendicular to the screen. Okay, so you see these interfaces, say down here, and they separate regions of about 10, alternately 10 and about 6 atomic spacings thick, inside which the deformation is essentially linear. And I've drawn that down here in the bottom right-hand corner. Now, what's actually happening to the atoms, if you look very carefully up here. So the cubic axes are one's into the screen, and the other two are at 45 degrees to the horizontal. And you see that to the left of one of these interfaces, the variant that's chosen is to stretch in this direction. But to the right, the variant is chosen stretches in this direction. Okay. So, and they fit together along this this approximate. It's an interface where everything is in its right position except exactly on the interface, or within one atomic spacing on either side of the interface. Okay, so that's a very typical picture of atomistically sharp interfaces for martensite. Here's another picture. This is again an electron micrograph, but at a lower magnification, so there we go, it's just 100 nanometers there. And now you see two such patterns. So on the left there's this family, this simple laminate of martensite, just like we saw in the previous picture, alternating between two different variants. And here's another one, and here's a third one, and they come together along a more complicated interface, which is sort of magnified in the inset there. So this is again cubic to tetragonal in nickel 65, aluminum 35. And these are at a lower magnification still. These are optical micrographs of copper, aluminum, nickel, which is a shaped memory alloy. And again, you see the same sorts of regions in which the deformation gradient is constant, separated by sharp, in this case, planar interfaces. And here is a slightly different one. Here we have what's more or less a simple laminate again, and another one down here. But they meet in another kind of approximate interface, and you see some sort of splitting of these layers as you approach this one here. So we're going to model this using elasticity theory. So we use this usual setup of continuum mechanics, reference configuration that a region omega in R3 that we use to label the particles x, and in the deformed configuration, I'm just going to be considering statics here. The point that was at x gets mapped to y of x. So y takes omega to R3, omega some bounded domain with some reasonably good boundary. I've colored in part of it in red because that's a part where I'll apply a displacement boundary condition. So we use energy minimization. We want to minimize an energy that depends on y through integrating over omega a free energy density that depends on the gradient of y at x and the temperature. The temperature is regarded here as a constant parameter, so I'm not talking about heat conduction or something. And the idea will be to try to find a deformation y that minimizes this integral subject to suitable boundary conditions. For example, that on the red part of the boundary y is prescribed to be a given mapping. Okay, now the deformation gradient at each point x can be identified with a 3x3 matrix, and in fact we would like it to have positive determinant to avoid interpenetration of matter. So the free energy density is defined for matrices of positive determinant, 3x3 matrices with positive determinant, and this is the notation I use with a plus here to indicate that the matrices have positive determinant, and it will depend on the temperature. And in order to encode the phase transformation into this continuum theory, it's convenient to look at the set of matrices which minimize the integrand at a particular temperature theta. Let's call that k of theta. And so here is a reasonable assumption for what k of theta looks like. So if we look at the middle line first, this is when you're actually at the critical temperature. So this is when you want the austenite and the martensite, the high and low temperature phase, to have exactly the same energy. So we're going to take the reference configuration to be the high temperature phase at the critical temperature. Okay, that means that at the critical temperature, y of x equals x should be a minimizer of the energy. So y of x equals x has gradient the identity matrix. So therefore you want the identity matrix to belong to k of theta at theta equals theta critical. But then if the identity matrix belongs to k of theta, any rotation times it should belong to k of theta, because doing a rigid rotation doesn't change energy. And so that's why you get, for this, this is the energy well at theta equals theta critical, SO3 rotations, which corresponds to the high temperature austenitic phase. Now in the low temperature phase, that's going to be described by capital N variants of Martensite, each one described by a positive definite symmetric matrix UI that depends on temperature. Here we're evaluating it, of course, at theta equals theta critical. And so that's the number of variants that you have, which has to divide actually 24, because that's the order of the cubic group. But so it'll be some number dividing 24. And again, you can pre-multiply by any rotation, because that doesn't change the energy. Now, above theta critical, we want the austenite to minimize the energy. So we have SO3 multiplied by a factor that represents thermal expansion. So alpha theta is just a number, and at theta critical it is 1. And below the transformation temperature, we want the Martensite to minimize the energy. Okay, so this is a way in which some information about the phase transformation is fed into the properties of the free energy density of C. So the UIs, the variants of the distinct matrices, if you take one of them, say U1, and you pre-multiply by Q and post-multiply by the transpose of Q, as Q runs through the cubic group, then you get, you won't get, this has 24 elements, but you won't in general get 24 distinct matrices, because some of them will coincide. And the number of distinct matrices that you get will be the number of variants, and those distinct matrices will be the UI of theta. So for example, for cubic to tetragonal, n would be 3, and the 3 matrices would be diagonal eta 2, eta 1. Eta 2 will be the longer length, say eta 2, eta 1, eta 1, and then you permute them to get the other 2. So those are the linear transformations that take you from the cube to the 3 variants. And so for cubic to orthorhombic, there's 3 parameters, alpha, beta, and gamma, and here are the 6 variants that you get for cubic to orthorhombic. The precise details are of course important when you do the calculations, but not important for this talk. Now we see lots of interfaces, so how are they described in this theory? Well, that's through the Hadamard jump condition. So let's think of having a piecewise affine Y, so that's a continuous mapping whose gradient is constant on either side of an interface. So the interface is given by x dot n equals k, so its normal is capital N, a unit vector. Above the plane, we'll suppose that the gradient is a matrix A, and below it a matrix B. And so we can apply the compatibility condition across the interface. That's just the expression of the continuity of Y, or equivalently the equality of the tangential derivatives on either side of the plane. So if you let C be the difference between A and B, then you must have, by the equality of the tangential derivatives, that Cx is 0 if x dot n is 0. But here's a typical vector which dotted with n is 0. Any vector z minus z dot n has inner product with n 0. So therefore C of this must be 0 for all z, and so C of z is the rank 1 matrix Cn tensor n times z. And therefore you get that C, which is A minus B, is a vector A tensor producted with n. And the vector is, of course, just Cn, A minus B acting on n. So that's the Hadamard jump condition. So it says that in order for this picture to be possible, A minus B, if A is different from B, A minus B must be a matrix of rank 1. And what's more, the second vector in that matrix of rank 1 will give you the normal to the interface. So now interfaces correspond to pairs of matrices with A minus B equals A tensor n. N is the interface normal. And at minimum energy, we want these matrices A and B to belong to this set K of theta, which you know. So it's just a calculation to check what the possibilities are. And here's well, it's not such an easy calculation actually. And here's a nice version of the answer, which you can express in many different ways. So suppose that you take two positive definite symmetric matrices, and you look at the corresponding energy wells SO3U and SO3V. Then they're rank 1 connected, namely there are pairs of matrices, one on one well and one on the other, which differ by a matrix of rank 1, if and only if the difference between U squared and V squared has the form a non-zero constant m tensor n plus n tensor m, where m and n are unit vectors. And there are exactly two rank 1 connections between a typical point on SOV, which you can take without loss of generality to be V, and SO3U. They're given by formulae, complicated formulae, I don't know what they are, but so there is some rotation R1 such that R1U minus V is a matrix of rank 1. But the interesting thing is that the normals, so there are two possible rank 1 connections from V to SO3U, and the normals are N and M, the same vectors that appear in this representation. So from this, you can deduce some very interesting facts. So first of all, there's no rank 1 connection between matrices A and B in the same energy well, because in that case, U squared is equal to V squared, and this is non-zero. So it's not possible to satisfy that. So secondly, if you take two Martin-Zittig variants, then the two Martin-Zittig variants, so UI and VI, then in order for this to have this form, it's necessary that, in fact sufficient, that the determinant of the matrix is 0, because this is a matrix over here of rank 2, so it's certainly necessary, and in effect it's sufficient too. And so therefore you get twins, that's these interfaces between different variants, and there are exactly two possible normals to these interfaces, and from this formula you see that the trace, because say these variants are similar with respect to orthogonal matrices, their traces are the same. So the trace of this matrix is 0, which means that 2C m dot n is 0. So it means that the two possible normals are orthogonal. Okay. And finally, suppose you take the austenite well, so SO3, and one of the martensite wells. Then if you check what the result tells you, it tells you that there's no rank 1 connection unless UI, the Martin-Zittig variant, has middle eigenvalue 1, which of course generically it will not do. But later we'll see what happens in this case when the middle eigenvalue is 1. Okay, and then some very exciting and recent experiments show that spectacular things happen. Okay, so in general you can't make an interface between austenite and a pure variant of martensite. So how do we understand microstructures? So that there are some sort of mathematical tools which I very briefly go over. So the first is weak convergence. This will be the most familiar one to most of you, I expect. So convergence of averages. So if you have a sequence of deformation gradients, dyj, so we're thinking of this sequence as perhaps being a minimizing sequence for the energy, a bounded sequence of gradients, so in absolute value dyj, this matrix has norm less than or equal to m for all j and all x, then dyj converges weakly to dy if when you integrate over any subregion of omega e, then the integral of dyj tends to the integral of dy. Okay, so this allows dyj to be oscillating very fast in j, and you can still get this kind of convergence. Okay. I'll show you examples later. So then the second, slightly more sophisticated tool is gradient Young measures. So suppose we're given a sequence of gradients dyj defined on omega, and I'm going to behave as if I was a microscopist. I'm going to first of all I obviously look at one deformation, so I fix J, and I fix the point where I'm going to look with my microscope, and I fix the aperture. So I look at a ball, center X, radius delta. Okay? And I look and see what the deformation gradient is at different points inside this little ball. Okay? So take a subset of matrices, and now we get a probability distribution on matrices depending on x, j, and delta, which gives you the probability of finding a particular value for the deformation gradient. So this probability measure, so the probability that you find a deformation gradient belonging to the set E is the volume of the points in the ball such that dyj of z belongs to E divided by the volume of the ball. That's what you're picking the point z at random from this ball. The probability of finding a deformation gradient which lies in E is given by this. So this is a probability distribution on 3x3 matrices. And now we let first of all j go to infinity. So if you're imagining dyj oscillating more and more finely, that will smear out the oscillations over this ball. And then you localize it by letting delta go to 0. And that should give you something which depends only on x. And you hope that it's still a probability measure on matrices. And under very general conditions, that works, provided you take a suitable subsequence of the original sequence of gradients. And that object, nu x of E, so it's a parameterized, it's a family of probability measures parameterized by the point x in omega. And that's called the gradient Young measure, generated by the subsequence of dyj. So let's see an example, a simple laminate, like we've seen already in the micrograph. So here, dyj is alternating between values a and b, and of course the a minus b has to be a vector tensor producted with the normal. That's a Hadamard jump condition. We'll suppose that the a layers have thickness lambda over j, and the b layers thickness 1 minus lambda over j, where lambda is something between 0 and 1, giving you the relative volume fractions of the a to the b layers. And now I let j go to infinity. So as j goes to infinity, this laminate becomes infinitely fine. Okay? So its weak limit will just be the average deformation gradient, namely it's a constant gradient, which is lambda a plus 1 minus lambda b. Now the gradient Young measure, so imagine doing what I said, take a point here, drawing a ball, picking a point at random, letting j go to infinity, letting x go to 0. So it's fairly obvious that when you do this procedure, you will have a probability lambda of seeing the matrix A, a probability 1 minus lambda of seeing the matrix B, and a probability 0 of seeing any other matrix. And for that reason, this gradient Young measure, in this case, does not depend on x, it's constant, and it's lambda a Dirac mass at A plus 1 minus lambda a Dirac mass at B. Okay, now the most complicated of these tools is quasi-convexity. In fact, nobody understands quasi-convexity, but it is nevertheless the central convexity condition of the calculus of variations. And here's the definition, so don't worry if it seems strange, because it seems strange to everybody. So an integrand f is quasi-convex at a particular matrix A if, whenever you take a smooth mapping Z, which on the boundary is given by AX, so it's linear with Z of x is A of x, A is our given matrix, that's on the boundary, then A minimizer of the integral of f of dz is the boundary data itself, namely z is identically equal to ax. Of course, the gradient of that is a. So we have the integral of f of dz of x is bigger equal to f of a, integral of f of a. And of course, that's just integrating a constant. So that's just the volume of omega multiplied by f of a. So it's a kind of Jensen's inequality for gradients. and it's quasi-convex if that holds at every matrix A. Okay, that's the condition, and there are deep connections between this definition and gradient Young measures. In fact, there's a characterization of gradient Young measures in terms of quasi-convexity. And the definition doesn't depend on omega, even though you might think it does. And roughly speaking, quasi-convexity is necessary and sufficient for the existence of minimizers in an appropriate Sobolev space of the integral of f of dy of x subject to suitable boundary conditions. And in particular, very widely used models of rubber are quasi-convex, so that minimizers exist. But for our problems here, the energy densities are not quasi-convex.
May I ask a question?
Yes?
What is the geometric picture of quasi-convexity? Do you have any?
The geometric picture of quasi-convexity. It's
Yeah.
well, there's first of all the the definition. Then there's saying that it's Jensen's inequality. When you say there's a geometric picture, one of the problems with quasi-convexity is that we don't know how to tell whether a given f is quasi-convex or not. Okay, so I'm not sure what kind of geometric picture you're thinking, but I mean, you know, I think the way I think of it, the most primitive way of thinking about it is, I've got this material, I specify linear boundary data. It's quasi-convex if the minimum energy is just linear, and nothing more complicated happens. Okay, and that's the difference between something like rubber in usual deformations and something like these materials. So for these materials, they're not quasi-convex, and if you minimize the energy with respect to linear boundary data on the boundary, then you get these very complicated geometrical patterns which are not linear. Okay. Don't have constant gradients. Okay, so C is not quasi-convex, take my word for it, and therefore you expect, and it's true, that the infimum of the energy in a suitable Sobolev space is in general not attained, and the minimizing sequences generate in the limit an infinitely fine microstructure. So it's exactly the lack of quasi-convexity that means that the minimum is not attained. To get closer and closer to the minimum energy, you have to introduce finer and finer oscillations in the deformation gradient. So if you like, the fact that the minimization problem does not have a classical solution is what predicts what you see, namely the existence of extremely fine microstructures. Right, well, now you can quasi-convexify things, both functions and matrices, sets of matrices. So if you take a compact set of matrices, K, for example, a bunch of Martin-Zittig energy wells, then you can define its quasi-convexification, KQC, which is the intersection of quasi-convex sets that contain it. So a quasi-convex set is the zero set of a non-negative quasi-convex function. Okay. Take all the quasi-convex sets that contain K, take their intersection, you get the quasi-convexification. So alternatively, you can take the centers of masses of all homogeneous gradient Young measures, that's gradient Young measures that don't depend on X, whose support lies in the set K. Or you can think of it as the set of macroscopic deformation gradients corresponding to microscopic deformation gradients in the set K. So in fact, this process of quasi-convexifying takes you from mesoscales to macroscales. And you go from the energy density to its quasi-convexification, and you go from sets of matrices to their quasi-convexifications. Right, now that was sort of preliminary material. Now I want to talk about austenite-martensite interfaces. So how, when you reduce the temperature, do you get from the high temperature phase to the low temperature phase? Okay. So here's a picture of how it usually happens. So this is in copper, aluminum, nickel, a picture of Chu and James, and you see on the right here you have the constant deformation gradient austenite. So this is cubic. This is taken at the critical temperature. And it can't make, as I told you, an interface between a pure variant of martensite with this. That's not possible geometrically. So it does the next simplest thing. It forms a simple laminate alternating between two variants. And if that's very fine, if you do a little kind of tweaking near the boundary here, boundary layer if you like, you can make that compatible with the martensite, and so that's what typically it does. And so according to mathematics then, this would be, the Young measure here would be a Dirac mass at the identity. Here it would be lambda Dirac mass A plus 1 minus lambda Dirac mass B, where A and B belong to the martensitic energy wells and are rank 1 connected. And the normal to this habit plane here is given by saying that the weak limit here, the deformation gradient of the weak limit, has to be compatible with the weak limit over here, which is the identity, namely that the difference between those matrices is a matrix of rank 1, and then the second vector, little m, gives you the orientation of the normal. Now, many years ago with Carsten Carstensen, we considered the possibility of having more complicated interfaces like this, where instead of in the martensite having a simple laminate, you might have something like a double laminate, like here, layers within layers, for example. And we did some calculations which were of the following type. So here you had the gradient Young measure in the austenite. Over here, we looked for a gradient Young measure that didn't depend on x, which was supported in the martensite wells. And so up here, the macroscopic deformation gradient, the weak limit is the identity. Down here, it's the center of mass of this gradient Young measure, and that belongs to the quasi-convexification of the set of martensitic energy wells. And then the F has to be the identity plus B tensor M. That's the compatibility condition. And the trouble is that since we don't know how to characterize quasi-convex functions, we don't know how to characterize this set either. And it's unknown unless there are only 2 martensitic energy wells. So this is a picture of a calculation. So these eta1 and eta2 were the 2 lattice parameters corresponding to the cubic tetragonal transformation. And in the light shaded region are the values of eta1 and eta2 for which you can make a classical austenite-martensite interface with a simple laminate, like I showed you. However, if you look in the union, if you're in the union of the dark and the light regions, you can make a more complicated non-classical interface with, say, layers within layers. Okay, so we were very interested in this, and we kept on asking people whether they knew materials for which the deformation parameters lay in the dark region and not in the light not in the light region. And well, people listened very sympathetically, but then they went on and did what they usually did, and so we didn't really get anywhere. But then we were part of a European program. By the way, the calculations also show that instead of getting a discrete number of interfaces, as you do in the classical case, you get normals that lie on arcs on the unit sphere. So you get many more possible habit plane normals if you're allowing these more complicated microstructures. So then there was a young Czech experimentalist, I'm going to show you 2 amazing experiments of his, Hannes Scheiner, who we belong to the same European project, and he learnt about rank 1 connections and stuff like that, and he devised the following way of producing these non-classical interfaces. So roughly speaking, he takes the austenite, he compresses it to form a single variant. This is possible to do. Turns the material around, presses it again, and then forms a twinned laminate. So this is copper, aluminum, nickel, 6 possible martensitic variants, and some pairs of these form what are called compound twins, and other pairs form what are called type 2 twins. So this is a laminate of compound twins that has been produced by mechanical means. So then he heated up this laminate from the corner. So it wants then to form austenite, right? But the calculations show that you can't make a classical austenite-martensite interface with a laminate of compound twins. The only ones you can, the only possibility is to make it with a laminate of type 2 twins. So it was conflicted. It had, on the one hand, it wanted to match onto this laminate of compound twins, And on the other hand, it wanted to make an austenite-martensite interface with other twins. And so what it did was a compromise. It produced, therefore, a double laminate, half of one and half of the other. And these are some pictures of these non-classical austenite-martensite interfaces where you see the, so over here's the austenite and here's this double laminate of martensite. And you can even make them curved, and we have some analysis of this. Now, I wanted to show this video. It's not my work, it's that of Dick James's group, but it is connected with what I was saying, and in particular the situation where the middle eigenvalue of the martensitic variant is exactly 1. And by analyzing this, so that's one particular mathematical condition, there's another one that allows other kinds of microstructures. And so Dick James's group found materials that satisfied all these mathematical conditions. Okay? And you get spectacular new materials this way, which have ultra-low hysteresis. So usually when you cycle a material, when you cycle the temperature around theta critical, there's a hysteresis of about 30 degrees centigrade. So it doesn't actually transform exactly at theta critical. You have to go, say, 15 degrees below, and then it transforms. And then when you heat it back up again, it won't transform at theta critical. It will transform maybe 15 degrees above. So that's a typical figure, about 30 degrees centigrade. These materials, because of these special features and microstructures, have a hysteresis of 0.2 of a degree centigrade, okay, which is really spectacular. So here's, and what's more, when you cycle them, across the critical temperature, amazing things happen that you just don't see in any other material. You get completely different microstructures forming on each cycle, okay? And we have no idea why this happens. Indeed, you would expect, I mean, it doesn't have to make any interface at all, but it chooses to make these very complicated patterns. Perhaps resulting from that it's a polycrystal, but I mean, so far experiments haven't been done in the single crystal case. Okay, so this was all over the BBC website sometime in October. Now I want to end telling you about another very interesting experiment of Hannes Scheiner, and I've worked with Kostas Komatos in Oxford on the analysis. What Scheiner did was to take a single crystal of copper, aluminum, nickel in the form of a prismatic bar, quite small, 12 by 3 by 3 millimeters, in the austenite, with its edges essentially parallel to the cubic directions. Okay, and now he compressed it along its longest edge, and just as in the previous experiment of his that I mentioned, you can form a single variant of martensite that way. So now I've got a constant deformation gradient in one of the martensitic wells. Now there's an effect, and in fact the analysis that we do is in some sense related to explaining this effect, called the mechanical stabilization of martensite. So that for some reason, when you reduce the load, it doesn't go back to the austenite, even though the austenite has less energy. Right? And it all depends on the geometry and the microstructure in the martensite. So this is one thing you can do, but another thing you can do is just take the austenite and cool it down, and then you'll get a very complicated microstructure of martensite. And then when you heat it up, it will transform back up to the austenite at a much lower temperature than the temperature you would need to make this go back to the austenite by homogeneous heating. So here's a picture of the specimen, and what he did was to touch it at various places with a soldering iron. Okay. So this is in the martensite. So now where you touch it with the soldering iron, of course that's going to make the temperature very high, and the austenite will have lower energy. So you're expecting the austenite to nucleate. Right? So you'd expect it to nucleate where you touch it with the soldering iron. However, that's not what happened. So if you touched the material at a corner, then it would nucleate at a corner. But if you touched at an edge or on a face, then it didn't nucleate underneath the soldering iron. Instead, there was a time delay, and it nucleated at a corner. So these are the temperatures I was talking about. So if you reduce the temperature homogeneously to form a martensitic microstructure, that would be complicated with lots of different interfaces. And then you started heating up again. Then the austenite would start forming at -6 degrees centigrade. That's the austenite start temperature, AS. And it would finish transforming at about 20 degrees centigrade. But for this thermally, for this, that's what's written down here is not what I meant to write. Okay, so but for the transformation from the mechanically induced martensite, that's this constant variant formed by compression, you would have to raise the temperature much higher than 20 degrees than for the thermally induced austenite. You'd have to raise it to 60 degrees, okay, and then it would transform. So that's already quite surprising. And the soldering iron has a much higher temperature still, 200 degrees. Okay. And so now I'm going to show you a video, but this is stills from the video, so you know what to look for. So there's the soldering iron in the middle of the face, right? And there's the nucleation happening in the bottom right-hand corner here. And you see it does so. You see there are two interfaces here, so we'll understand that in a moment. And then the martensite. So this is now martensite. This is now austenite, and this is martensite. And so you see that the austenite will gradually eat up the martensite. So here's the movie. Maybe I'll play it twice because it's the most interesting thing. Okay. So if you look at the bottom right-hand corner, yeah. Okay, try again. And you see the big angles on the top left-hand corner, how it finally becomes, and those two interfaces, they're just, still hasn't eaten it. Now it's eaten it all up. Okay, so I play it once more. Action replay. Okay.
So you're starting with
martensite, pure variant of martensite.
What's so special about the bottom right-hand corner?
It could start at other corners. It probably depends on where you touch it. Maybe it's the corner that's nearest, but it's also there's some crystallography involved, so it's not maybe quite just that. So anyway, this is our proposed explanation that nucleation. So it's geometry again. It's just not possible to nucleate in the interior or on a face or on an edge, because you can't geometrically match the new low temperature phase with the old one. Okay. And we articulate that in a sort of simplified model by showing that if U sub S is the deformation gradient corresponding to the pure variant of martensite, then the free energy function is quasi-convex in the interior, at the boundary faces and at the edges, but not at a corner. So this in some sense says in this simplified model that nucleation, if nucleation is localized, it must occur at a corner. Okay. So now to make the more, so now we make the problem a bit too easy maybe, but we're going to assume that the energy is infinite unless you are on the wells. Okay. So there is some way of justifying this in terms of a gamma limit, but of course it's clearly an approximation. And now we're going to define the energy for microstructures. So our unknown is going to be a gradient Young measure that represents the microstructure. And so the energy now is given by the integral over omega of the expectation under the Young measure of the energy density. And the energy density is going to be 0 on the martensite wells by hypothesis. We're thinking of having a high temperature here, so we want the austenite to have lower energy. So on the austenite, the energy is going to be minus delta with delta positive. And this approximation that elsewhere it is going to be plus infinity. And so the domain, if you like, of this function W, where it's finite, is the union of the austenite and the martensite energy wells, and elsewhere it is infinity. So nucleation is impossible in the interior. I'll just give you the statement of what the theorem says. So if you take a ball in the material, okay, and in this ball you require that the support of the gradient Young measure is contained in K, so that's austenite or martensite, and elsewhere it is the initial variant, then I of nu is bigger equal to I of the direct mass at U sub s. So that's quasi-convexity at U sub s. It says you can't nucleate in the interior. Similarly for edges and faces, so if you take an intersection of a ball centered a point on a face, do exactly the same thing, or the intersection of a ball centered at a point on an edge, then in both of those cases you can only increase the energy by introducing the austenite, even though the austenite has lower energy than the martensite. And this is geometry that is preventing this happening. On the other hand, at a corner you can do the following. So here is the initial martensitic variant, and you make it be one of the deformation gradients in a simple laminate corresponding to a classical austenite martensite interface. So in yellow you have a constant rotation, that's the austenite. Here you have a simple laminate, one of the gradients being U sub s and the other being some other rotation, and you show that you can reduce the energy this way, and so I is not quasi-convex at a corner.
If you have different angles in different places.
Different. Okay, so if you cut the specimen differently, then we don't have a complete picture. We know that there's a very large set of normals at which the energy is not quasi-convex at a face, but not all normals. I mean, that's probably a failure of our technique rather than a failure of, but we don't know. So as long as if we cut a parallel pipette, as long as it had normals to the interfaces which are in this large set of things that we can calculate, then this would theoretically happen. Okay. So you can ask,
Just thoughts on that experiment. That's martensite.
Could we let John finish?
I have finished, don't worry.
Have you?
Yeah, I finished,
Okay.
don't worry.
And I will take some questions. Sorry.
Since that bar was martensite that you showed on the video, there's no possibility, is there, that the thermal conductivity of this non-cubic phase is sufficiently anisotropic, so when you touch that soldering iron to the bar, you're not getting a nice.
Well, no, I mean the explanation for the time delay is that it's heat conducting, of course, and that when you wait until one of the corners has a sufficiently high temperature for the austenite to be nucleated there.
Right.
Now, what's less clear is why this doesn't happen without you touching the specimen with a soldering iron. Because remember, as I said, that if you just homogeneously heated this,
Right.
it would take you up to 60 degrees, which is much higher than the energy at which the austenite has lower energy. Okay, and actually, when you do that, you still see that nucleation occurs at a corner. So the only thing I can offer to explain that is the following: that if you imagine, if you idealized the martensite, so suppose you thermally induce the martensite, so then that means that you've got a very complicated microstructure here. So if you idealize that by thinking that it was a simple laminate, right? Then what would you need to do to introduce a volume V of austenite? So the natural thing to do would be to bring in an austenite-martensite interface from here. Okay. Now, when you do that, you gain energy delta, which is the difference between the austenite and the martensite, times the volume V. But you also gain the energy, the interfacial energy, from these interfaces, which are now no longer here. Okay. So it's plus something. That's the loss of energy. Whereas in this case, you again drop down by delta V because you've reduced the energy. You know, you've got that region where there's the austenite, but now you've got to introduce new interfaces to match onto the martensite. So now I have minus something. So that suggests that it's easier to nucleate things in this case than it is in this case.
John, is there any chance that, I mean, this is a macroscopic chunk of material, there are doubtless various kinds of dislocations around, each of which have cores and very, very high local strains. Can they play a part in the nucleation of this? Because, you know, depending on how this bar was prepared, there may be a collection of these dislocations in this single variant martensite. Locally, the strains can play a huge role in triggering the release of the metastability.
But if that was happening, you'd expect it to be triggered in the interior or at a face. So the interesting thing is it's not triggered there. Okay, I'm certainly not an expert on dislocations, but the word on the street from the people who do these experiments is that there are not that many. I mean, relatively speaking. I mean, to others. Yes, I know, but in terms of the number of, you know, relative to the number of atoms, so they don't think of that as. I mean, of course, in other situations, what you say is exactly correct, that you'll get nucleation from dislocations and so on. Okay.
Which obviously the existence of this position-dependent temperature, transient and heterogeneous in space, is critical for this. The fact that the temperature is not uniform in the sample.
No, I don't think so, because as I say, if you homogeneously heat the variant, it will transform at a corner, even though the temperature is constant. So it's the geometry that's determining where the nucleation takes place.
So the experimental result by Dick James and Tom Ship, it's about creating this austenite-martensite interface, right? According to one of the theorem of propositions you mentioned, that you needed to have middle eigenvalue.
So the middle eigenvalue is 1, and so-called cofactor conditions are also satisfied.
So what they do, they just adjust these lattice parameters?
That's right. Okay, so of course the lattice parameters depend on the composition of the alloy. So the first thing that they did was to there are people whose names I forget, but there are chemists who are specialized in being able to test, say, 100 different compositions of an alloy simultaneously. I can't remember what the name is now, but there's one of them involved in this team. So it's an art. It's not a science. You can't. I mean, it's an inverse problem how the deformation parameters depend on the composition. But what you're doing is you're changing the composition, you know, and seeing what happens, and then you go in that direction and so on. And then they plotted the hysteresis against the middle eigenvalue, and they found an incredibly sharp cusp like this. So this was the first thing that they did, and very, very sharp. And there's some sort of more or less, well, there are some theories which predict the shape of this cusp based on the playoff between interfacial and macroscopic and elastic energy. So then they did these more sophisticated things to try and get the cofactor conditions to hold as well.
Okay, if there are no further questions, let's thank you once again for